I'm going to look at the net force and the net torque on a loop of wire that's carrying a current. So in this example, it's a rectangular loop, one side B, the other side of length A, carrying a current around counterclockwise. We have a magnetic field that points to the right. This idea of what's the force and the torque on a current loop, this is at the heart of a electric motor. The dashed line is there to indicate the axis of rotation for the loop, so what direction it can spin. So we're going to go through and calculate what the direction of the magnetic force is on the current on each of the four sides. So the current at the bottom is going to go to the right. That's the same direction as the magnetic field, so that's no magnetic force. The right side of the loop, I have a current that's going up the page, a magnetic field to the right. So that's going to give me IL cross into B. It's going to give me a magnetic force into the page. The top of the loop, the current is going the opposite direction as the magnetic field, so there's no force. And then on the left side of the loop, I have a current down the page, magnetic field to the right. So then I have a magnetic force that's going to come out the page. So two sides of the loop have a force on them. They're current of the same size, and the length of the wire is the same. So these forces are the same magnitude, they just point in different directions. So the net force is going to be 0, which is good. You don't want your electric motor just jumping out of your car. But there is a net torque. You can calculate how big the torque is in this example. The torque is going to be the magnitude of the lever arm, which is half of B, and that times the force. So there are two contributions to the force. They're going to be I times the length A times B. And in principle, I might have not just one loop of wire, but I could have N of them. So that would be the number of turns, capital N. And the 2's cancel out. And we'll have a torque given by the current in the loop times A times B. So that's going to give me the area of the rectangle times the number of turns times the uniform magnetic field strength. So that's the area of the loop. So I times A, the area, times the number of turns, times the magnetic field strength will be the torque. And this is a case where you're getting the maximum torque, because the area of the loop is a vector that points perpendicular to the loop, so that's coming out of the plane of the page. The magnetic field is pointed over to the right. Now I want to get a more general expression for this. So what we're going to do next is I want to think about what this looks like if I'm viewing it from here. So I'm at the side looking along the rotation axis, and we're going to consider a tilted loop. So we can get an expression for the torque that actually involves that angle. So we'll try that next. So here I have the loop at an angle. Let me step through this a little bit. So we're looking along the direction of the rotation axis. So the long ends of our rectangular loop are coming out of the page and then going into the page with the currents. The area of the loop points along the normal direction perpendicular to the loop, and that's going to be inclined at an angle of theta relative to the magnetic field. All right, so we look at the magnetic forces now. At the top of the loop, I have a current coming out, magnetic force or magnetic field to the right. So the magnetic force is pointing up. And here at the bottom of the loop, I have a current going in, magnetic field to the right. And so the magnetic force is pointing down, straight down. Okay, so these forces are going to give us the line of action for calculating the torque. So when we write out the torque, we're going to have, there are two forces that are equally strong. So again, the net force is still 0. We'll have 2 times magnitude of the current, the length of the wire that's carrying the current that the force is exerted on, the magnetic field strength, and then we're going to have the lever arm for the torque. So half of the length B times sine of theta. That will be our net torque on the loop. Writing that out and canceling out the 2's again, we're going to have the current times the area of the loop times the magnetic field strength B times sine of theta. And if I have n turns, then we'll have a torque goes n times bigger. Current times the area of the loop times B times sine of theta. And we can look at that expression and think about when the torque is going to be biggest, when it's going to be smallest. So what we had in the original orientation, so we draw that out. There's our loop viewed edgewise. There's the normal to the loop and the magnetic field to the right. That's going to be the orientation where that's at 90 degrees, where we're going to get the maximum torque. So plus n times I times A times B. The minimum torque would be where it's minus 90 degrees, so I'll get minus 1. We could also think about the orientation that's going to give us no torque. So if I draw that out, that would be my loop viewed on edge. There's the normal direction to the loop, and magnetic field is parallel. So the angle between the loop and the magnetic field is 0, and if I put in 0 for theta, I'm going to get a torque of 0. So that happens at 0 degrees. It also happens at 180 degrees. So that torque going to 0 twice during a rotation and reversing signs, that is why in an electric motor you're going to need to reverse the direction that the current flows with a commutator or some mechanism. It's much easier to flip around the direction of the current from going clockwise to counterclockwise, clockwise to counterclockwise, because this magnetic field is usually coming from a permanent magnet. So you need something much more complicated to flip the magnetic field around. But if you flip the direction of the current, I can get a torque that's always going to be in the same direction.